रेनो को ऑफिस जाएगा अभी, रेनो वाला रिसीव देगा।
and you can see another one near this picture from the downstream side. So you can see the downstream of these undersluice gates. So these are the divide walls. This is one, and you can see another one near distance. As you can see here, so I was standing on the guide bank or that embankment. This guide bank goes like this to a large distance upstream. And this is the head regulator. There is a small bridge to cross to the other side. Here you see the canal. The canal also, you can see it's not very well maintained, and there is lots of sedimentation. And as you can see, I guess on the left hand side, there is some erosion from the embankments of the canal also. So that has also filled up some portion of the canal. And these are the gates. These are the machine arrangements which are connected with cables, as you can see. And these cables run downwards and they are attached to the gates. So these gates can be raised or lowered as per necessity. Now let's look at some other aspects. I think this model is a little bit more to the scale than the previous lecture. So this is a very wide river, let's say. And this is the fish ladder. This is the weir. This is the one divide wall. Here also you can consider it a divide wall. And these undersluice gates, the number of these gates or the size of these gates will depend on the highest amount of flood that needs to be released when that flood comes. So here I've only shown 4 gates, but if the highest flood is of very large magnitude, then maybe we would have to provide some more gates here so that when flood comes, we have a larger discharge capacity so that the upstream is not flooded. Now, let's discuss some more about these undersluice, the silt excluders. See, they have a very peculiar arrangement. These are long tunnels. The tunnel very close to this head regulator through which water is transferred to the canal. That is the longest canal, and as we move away, as we move away from that, these tunnels become shorter and shorter. The reason behind that is when water goes into these gateways, they have a component, velocity component like this. And if we had made all these tunnels of same length, then because the velocity is happening this way, then all these tunnels water will not enter these tunnels and they will flow perpendicularly. Once we are making once we are adjusting the tunnel lengths so that this tunnel is the longest and this tunnel is the shortest and so on. So in that case, because the water velocity is in this direction, then a major part of the lower portion of the flow will enter these tunnels, and therefore along with that, sediments or the silt will be trapped inside these tunnels. Sometimes these tunnels may not be necessary if the natural riverbed is much below the sill level. Sill means this level that is the threshold of this head regulator, is called the sill. If the river bed itself is much lower, suppose 2 or 3 meters lower than this level, then these kind of sill excluders are not needed, because the lower part is already much lower than the sill level. So therefore the sediment which is carried by the lower portion of the current will not be able to enter these gateways. So this is how, these are some of the facts that I wanted to add in continuation to the previous lecture. And one more thing that I forgot to mention is that you see these cut-off walls or the sheet piles. These are provided here so that water doesn't simply flow straight from this point to the downstream end of the impervious floor. And because of provision of these kind of cutoffs, they'll have to take a longer path. They have to first go down, then up, then again horizontally, then again in this cutoff they'll have to go down, then up. So it increases the length of flow. But one problem may be that what if the water just water in the side of the work of the this impervious floor, that is on the edges, on the right hand side and left hand side, this water can directly go from here to here, and that can be prevented by extending these cutoffs to a considerable length and inserting them into these embankments, so that when water tries to take this sideway, it also has to again go through this longer path, because there will be cut off in the horizontal direction also, and therefore the leakage will be reduced. So that's all for this one. Thank you.
Good morning, students. Today we'll continue again with unit number 4 and topic number 8, which is diversion headworks. So, diversion headworks. It was stated earlier that the main permanent canal forming the primary part of a direct irrigation scheme takes off from a diversion weir or a barrage. In fact, these permanent canals take off from rivers, and the arrangements are so well made at their heads that a constant and a continuous water supply is ensured into the canal even during the periods of low flow. The works which are constructed at the head of the canal in order to divert the river water towards the canal so as to ensure a regulated continuous supply of silt-free water with a certain minimum head into the canal are known as diversion headworks. Next, weir and barrage. In general, the above purpose can be accomplished by constructing a barrier across the river, so as to raise the water level on the upstream side of the obstruction, and thus to feed the main canals taking off from its upstream side at one or both of its flanks. The ponding of water can be achieved either only by a permanent pakka raised crest across the river or by a raised crest supplemented by falling counterbalance gates or shutters working over the crest. If the major part or the entire ponding of water is achieved by a raised crest and a smaller part or nil part of it is achieved by the shutters, then this barrier is known as a weir. Figure I'll be showing in the next slide. On the other hand, if most of the ponding is done by gates and a smaller or nil part of it is done by the raised crest, then the barrier is known as a barrage or a river regulator. So this is the figure of a weir. This video we have already seen in our last class. And this is the figure of a barrage, also known as a river regulator. We have also seen a video related to this. So if most of the ponding or the entire ponding is done by a permanent raised crest, as in a weir, then the efflux caused during high floods is quite high. On the other hand, if most of the ponding is done by gates, as in a barrage, then the gates can be opened during high floods and the efflux, that is the rise in HFL near the side, will be nil or minimum. Hence, the latter device, that is the barrage, gives less efflux and a better control upon the river flow, because the inflow and outflow can be controlled to a much greater extent by suitable manipulations of its gates. So moreover, a gate control weir, that is the barrage, can be provided with a roadway across the river at a small additional cost. The choice between a weir with shutters and one with counterbalance gates, that is a barrage, is largely a matter of cost and convenience in working. A shuttered weir will be relatively cheaper but will lack the effective control possible in the case of a barrage. Moreover, a barrage-type construction can be easily supplemented with a roadway across the river at a small additional cost. Hence, barrages are almost invariably constructed these days on all important rivers. Next, gravity and non-gravity weirs. When the weight of the weir, that is its body and floor, balances the uplift pressure caused by the head of the water seeping below the weir, it is called as gravity weir. On the other hand, if the weir flow is designed continuous with the divide piers as reinforced structure such that the weight of concrete slab together with the weight of divide piers keep the structure safe against the uplift, then the structure may be called as a non-gravity weir. In the latter case, RCC has to be used in place of brick piers, but in particular cases, considerable savings may be obtained as the weight of the floor can be much less than what is required in a gravity wire. So here it is a picture of gravity wire on the left, and on the right it is the picture of non-gravity wire. So this is a layout of a diversion headworks and its components. So a typical layout of a canal headworks is shown in figure 9.5. Such a headwork consists of weir, proper, under sluices, divide wall, dividing the river width into two portions. One is called the weir portion, and the other portion from which the canal takes off is having openings and is called as the under sluice pocket or under sluices or weir scar sluices. If there are two canals taking off from each flank, then there will be two divide walls and two under sluices. River training works such as marginal bunds, guide banks, groins, etc. Number 5, fish ladder. Number 6, canal head regulator. 7, weirs, ancillary works such as shutters, gates, etc. And number 8, silt regulation works. So this is your assignment for lecture number 32. You have to write a case study on the Columbilly irrigation of Australia. I repeat, you have to write a case study on the Columbilly irrigation of Australia, and the last date is already mentioned here. Regarding this, I have already shown you a video earlier. That is why this assignment. At the same time, now you can give your attendance in the chat box and also go through a video that we'll watch now. That's all for this lecture. Thank you.